In this lecture, we're going to talk about how we can use graphing calculators to solve systems of linear equations. We're also going to take some time to talk about special cases, systems that have no solutions or infinitely many solutions. Our process for solving systems of linear equations with the calculator will start with a matrix representation of the system. So to practice, I want you to pause the video and see if you can represent the system on the screen here with a matrix. The matrix representation of this system would be as follows. I'm going to copy the coefficients of the first equation, 1, 3, -5. And then we're going to use this line segment to divide the coefficients from the numbers on the other side. That's where the equal sign falls. And then we'll write down the 1. The next row would have entries of 2, -1, 4, and 9. And the last row would have entries -3, 4, -1, -16. This winds up being a 3 by 4 matrix. In a previous lecture, we talked about how we could use matrices to solve systems like this, and we did all of that arithmetic by hand. We methodically eliminated variables by creating zeros on the left side of this matrix, and we used that to solve the system. Most modern graphing calculators have a way to input a matrix into them, and then we can have the calculator put this into a form where we can find the solutions, and that's what we're going to discuss first. Rather than just representing this system, let's solve this system. So let me copy the matrix that we just came up with. Let's talk about how we put this into the calculator. There are a couple of different options, but I'm going to show you what I think is the most straightforward way. If you look carefully over the fourth button down the left side, you should see the word matrix in the same color as your second key. So I want you to push second and that button, and you should see 3 headings: names, math, and edit. We're going to start by editing one of these matrices. So I want you to scroll to the edit option. And in my demonstrations, I'm always going to be editing matrix A, but you can pick different matrices if you want. So I'm going to press the 1 key to select matrix A. You can see that I'm editing matrix A. And the first thing we have to do is tell the calculator what size we want this to be. The first number is the number of rows, and the second number is the number of columns. We said that this was a 3 by 4 matrix because it has 3 rows and 4 columns. And so I'm going to enter a 3, hit the enter key, and you can see that we now have 3 rows. And then I'm going to type a 4, hit the enter key, and you can currently only see 3 columns, but these little underscores here are indicating that there's more information that we can't see right now. There's at least 1 more column that's off the screen. At the bottom of the screen, you see this 1, 1. That's indicating that we're in the first row and the first column. And the number in the first row and first column is a 1. Let me move my calculator emulator over a little bit. So the first entry is 1. And then you hit enter and it will move across the row. So now we're in the first row, second column, which is a 3. And then first row, third column is a -5. Make sure you use the little negation key for negatives. Now you can see we've shifted over to the right edge of the matrix. These little brackets are indicating that we're on the right end, so this is the last column. I know you can't see it right now because my emulator is covering it, but the number on the right side of the first equation was a 1. So I type a 1 and then hit enter and it will take us to the second row. You can see the entries here are 2, -1, 4, and you can't see the last entry, but it was a 9. And then for the third row, -3, 4, -1, and you can't see it right now, but the last entry was -16. Make sure you hit enter on this very last entry. If I hadn't hit enter on the -16, it would have remained a 0 when I jump out of the matrix screen. And that's the next thing we're going to do. We're going to quit back to the main screen. Above the mode key right here, you see the word quit. That's going to take us to the main screen. So second and the mode key to go back to the main screen. And now we're going to ask the calculator to do some matrix math. So second matrix again. And now we're going to go to the math heading. Notice, by the way, that matrix A is now a 3 by 4 matrix because we've edited it. We've changed it to the matrix that we want. So I scroll to the math heading. The choice we want is reduced row echelon form, which puts 1s down this main diagonal and 0s everywhere else. So the left side of the matrix will say 1, 0, 0, 0, 1, 0, 0, 0, 1. And the reason we want it in that form is that just tells us the values of x, y, and z. The calculator calls this function rref and it's choice B. You can actually get to it faster if you scroll up. rref, reduced row echelon form. I'm going to select that option. And now we need some input. We have to tell the calculator which matrix we want to put in reduced row echelon form. So one last time, back to the matrix options, second and that X inverse key to access the matrices. We need to put in the name of the matrix we're using, and we're using matrix A, so I need to select the first option. You can do that by hitting the 1 key, or you can hit the enter key because the colors are inverted on that option. You're supposed to close the parentheses, you really don't have to. And when you hit enter, the calculator is going to put the matrix in reduced row echelon form. So the first row says 1004. Remember that our matrix is an augmented matrix and we're separating the coefficients from the numbers on the right. So this says 1x plus 0y's plus 0z's is equal to 4, or in other words, x equals 4. It's just telling us the value of x. X is 4. The second row says 0x's plus 1y plus 0z's equals negative 1, so y is negative 1. And the last row says 0x plus 0y plus 1z equals 0, so z is equal to 0, which tells us that the solution is 4, negative 1, 0. Let's check this solution. 4, 3 times negative 1 would be 4 plus negative 3, that's 1. 5 times 0 is 0, and 1 minus 0 is 1. Yeah, it works there. 2 times 4 is 8, minus negative 1 would be 9, plus 4 times 0 would still be 9. And negative 3 times 4 is negative 12. 4 times negative 1 is negative 4. Negative 12 plus negative 4 is negative 16. Minus 0 is negative 16. Yes, this is the solution. Let's try another one. We're going to solve the system 6x plus 6y minus z equals 3, negative 2x plus 3y plus 8z equals 33, and 10x minus 9y plus 2z equals 7. Your first job is to rewrite this in matrix form. Do that for me, please. The matrix representation of this system would be 6, 6, negative 1, 3 in the first row, negative 2, 3, 8, 33 in the second row, 10, negative 9, 2, 7 in the third row. If we were doing this by hand, I'd have my eye on this negative 1 to eliminate the z's, but we're going to do this with the calculator. Let's bring the calculator back up. I'm going to access those matrix options, second and the X inverse key. I'm going to continue to edit matrix A. You could instead use some of these other options if you want to save one of these matrices for later. I'm going to scroll to the edit option, select matrix A. It's already 3 by 4, so I can skip past these by just hitting enter twice. Enter, enter. And now I'm going to put in the new matrix. So 6, enter, 6, enter, negative 1, enter. And the output there was 3. Negative 2, enter, 3, enter, 8, enter. And the right side of that equation was 33. 10, enter, negative 9, enter, 2, enter, and the right side of that equation was 7. Make sure you hit enter on that last one. We're going to quit back to the main screen with second and the mode key. We're going to pull up the matrix options again, second X inverse. Scroll to the math heading, and we want choice B. And we could scroll up to get it again, but there's a shortcut to selecting these letters. If you look carefully above most of the buttons, there's a green letter, same color as your alpha key. If you know you want choice B, you can just push the alpha key first, and then this apps key, and that will take you to choice B, reduced row echelon form. If you just want to play it safe, you can just scroll up or down to choice B, rref, reduced row echelon form. One last time to those matrix options, second and the X inverse key, matrix A. And we get a weird answer here. We see some decimals. X is 0.5, you know that's 1/2. Y appears to be 0.6 repeating, which is 2/3, and Z is 4. I want to show you that we can get the calculator to tell us what these fractions are, and you do it the same way that you get it to change any decimal to a fraction. Push your math key. The very first choice says change my output to a fraction. Now that doesn't really make sense here, but what it's going to do is change any decimals in our representation to fractions if possible. And when I hit enter, it gives us the fraction representations of the values of x and y. So our solution is 1/2, 2/3, 4. Let's at least verify that that works in the first equation. 1/2 of 6 is 3, 2/3 of 6 is 4, 3 plus 4 is 7, minus 4 really is 3. I'll leave it to you to check that it works in the other two. We're going to need some repetition to learn this calculator function, so let's try another. Here we've got the system 5x minus 6y plus 3z equals 4, negative 2x plus 3y plus 7z equals negative 6, and 4x minus 9y minus 9z equals 3. I want you to pause the video and see if you can remember all of the steps. First, come up with the matrix representation of the system, and then see if you can remember the calculator steps for inputting the matrix and getting the reduced row echelon form. Here's the augmented matrix that we would use to represent this system, and now I'm going to put that into the calculator. I hit second and the x inverse key to pull up the matrices, and the first thing you need to do is go to the edit option. We're going to edit matrix A, which is still a 3x4. We're going to type in each of the entries. We're going to go across the rows as we hit enter. So 5, enter, negative 6, enter, 3, enter, 4, enter, negative 2, enter, 3, enter, 7, enter, negative 6, enter, 4, enter, negative 9, enter, negative 9, enter, and 3. Make sure you hit enter on that last entry. Now I'm going to quit back to the main screen with second and the mode key. One shortcut you could use here, since we're doing the same thing over and over again, is to hit second enter. If I hit second enter, it'll bring my last input back on the screen. Now that's not what I want to do, but if I hit second enter again, it will bring back up that command reduce row echelon form of matrix A, which is exactly what we want. So if you're repeating the same steps over and over in your calculator, you can hit second enter to cycle through your last few inputs. However, rather than using that shortcut, I want to show you how you access reduced row echelon form so that you're ready to do this on an exam. So let me do this without that shortcut. After you've edited the matrix, you're going to hit second and the x inverse key, and this time you're going to say we want to do some math. So go to the math heading, and we want option B, rref, so alpha and the apps key. And then one last time to the matrix options. This time I put in the name of the matrix at matrix A. Choice 1. And we get really nasty answers. Let's change these into fractions. Math, choice 1, enter. And so our solution is this ridiculous ordered triple 159 over 46, comma 259 over 138, comma negative 31 over 46. You can imagine what a hassle that would have been to come up with by hand. Here it just took a few button presses and we were home. The next example looks like the previous three, but when we get our output, you're going to notice something fishy going on. I want you to try to do this one as well, but you'll notice something strange when you get to that last step. So here's the matrix representation of our system. I'm going to put that into the calculator. So I've got all my entries in the calculator. I'm going to quit back to the main screen with second and the mode key. Second and the x inverse key. I want to do math, and in particular I want to put this in reduced row echelon form. Alpha and the apps key will select option B. You can also just scroll to it. One last time to the matrix options. I'm going to put in the name of the matrix. I hit enter, and you notice something different right off the bat. This first row isn't 1, 0, 0. It's 1, 0, and then some ridiculous decimal. And the last row also should stand out as well. It says 0, 0, 0. So that we can see the whole matrix, let me change this to the fractions. That last row is where we've really got something strange going on. Look at what it says. It says 0 x's plus 0 y's plus 0 z's equals 1. That says 0 equals 1. That's not possible. 0 is not equal to 1. That's a contradiction, and therefore the system is inconsistent and has no solutions. When a system has no solutions, you'll notice that in the last row, the left side of the matrix will be all zeros, and on the right side you'll have a 1. That very last row says 0 equals 1, which is a contradiction, and therefore this system has no solution. The graphs of these equations are actually planes, two-dimensional surfaces. In all of our previous examples, those three planes have intersected at a point. These three planes don't intersect at a single point. You can tell that in the matrix representation because we have a string of zeros equal to a non-zero number. That last row says 0 is equal to 1, which isn't true. Basically, it's saying the only way the system could have a solution is if 0 is equal to 1. But 0 is not equal to 1, and so the system has no solution. That's one of the special cases that you can run into. We've seen this in the 2x2 systems. This can happen for any number of variables and any number of equations. The other special scenario we ran into before was infinitely many solutions. The system on this screen has infinitely many solutions. X plus y minus z equals 0, x plus 4y plus 2z equals 0, and 2x plus 5y plus z equals 0 is a system with infinitely many solutions. You can certainly see that it has at least one solution because if x, y, and z were all 0, then all of those equations would be true. But it turns out there are other solutions. And what we're going to do is find a general solution, or what I'm going to refer to as a recipe for all of the solutions. And then we'll use it to come up with specific solutions. First, let's get the matrix representation here. 1, 1, negative 1, 0, 1, 4, 2, 0, and 2, 5, 1, 0. Let's put that into the calculator. Make sure you hit enter on that last entry. Quit back to the main screen. Back to the matrix options. We want to do some math, and in particular we want to put this in reduced row echelon form, which is choice B. Back to the matrix options. Put in the name of the matrix you want to put in reduced row echelon form. And you'll notice something strange again. We get a row of zeros on the left side, but this time it's equal to 0, not 1. That's a true statement. We call that says 0 equals 0. That's an identity. Let me write down the reduced row echelon form here. This last row is what gives away that there are infinitely many solutions. But this time we're going to take this further. We're not just going to stop with the fact that there are infinitely many solutions, but we're going to come up with a general solution, a recipe for generating all of the solutions. The way I'm going to do that is to translate each of these first two rows back into equations. The first one says x minus 2z equals 0, and the second says y plus z equals 0. In both of these equations, I'm going to replace the z with a c, and I'm choosing c to be some arbitrary constant, any number that I want. You can pick another letter besides c, like you can pick a. You can't pick x, y, or z because those are the variables. You probably don't want to pick I because we use that for a specific purpose. I'm picking c to represent a constant, any constant. So in the first equation, I get x minus 2c equals 0, and now I can solve that for x. I get that x equals 2c. I can do the same thing in the second equation. I'm going to get y plus c equals 0, and solving that for y, I get y equals negative c. So my x-coordinate is 2 times c, my y-coordinate is the negation of c, and my z-coordinate is c, because I let z equal c. And this is a recipe that will generate every solution to this system. For example, let c equal 0 in our general solution in our recipe. If c equals 0, then I get 2 times 0, which is 0. I get the negation of 0, which is 0, and I get 0 at the end. And 0, 0, 0 is the solution that we just eyeballed at the beginning. Maybe not super interesting. Let's come up with another one. I'm going to let c equal 1. If c is 1, I get 2 times 1 is 2. The negation of 1 is negative 1, and then 1 for c. So 2, negative 1, 1 should be a solution to all three equations. Let's check it. 2 minus 1 is 0. Yes, that worked. 2 minus 4 plus 2 is 0. Yes, it works there. 4 minus 5 plus 1 is 0. That's another solution. Let's let c equal negative 5. Then we get negative 10, comma 5, comma negative 5. Negative 10 because it's 2 times negative 5. The opposite of negative 5 is 5. And then the z-coordinate is just whatever c is, so negative 5. Now how did I know to choose negative 5? You can pick any number you want. I just picked negative 5 to get something a little bit different. I didn't want to just go 0, 1, 2, which is a good way to do this. So I picked something a little bit strange. Will this really work? Negative 10 plus 5 minus negative 5 is 0. Yes, that's true. Negative 10 plus 20 minus 10 is 0. Negative 20 plus 25 minus 5 is 0. This one works too. You can pick any number you want and generate the solution. I want you to practice this by generating a solution for me. You're going to let c equal 8 and tell me what solution that gives us. Plugging 8 in for each c, we get 16, negative 8, 8. I'm not going to check all of these, but let's just check the last one. 2 times 16 is 32. 5 times negative 8 is negative 40. 32 minus 40 is negative 8, and negative 8 plus 8 really is 0. For each different c you pick, you get a different solution. And so you're going to get infinitely many solutions for all of the options that you pick. And of course, I'm being boring and just picking integers, but you could be cool and pick a fraction or pick an irrational number like pi or e, right? Tell me that wouldn't be cool. It'd be awesome. Let's go through the logic one more time. We saw that this had infinitely many solutions because the last row says 0 equals 0. When there's no solution, the last row will say 0 equals 1. But this one has an identity at the end, 0 equals 0. I also told you that it had infinitely many solutions, but that's verified by this last row. We then translated the first two rows into equations, and we plugged an arbitrary constant in for z. The reason I plugged it in for z is because it occurred in both equations, so I could solve for the other variable. That gave us a recipe. The x-coordinate had to be 2 times c, the y-coordinate had to be the opposite of c, and z was equal to c. Then we just picked some numbers and plugged it in for c to get some specific solutions. Let's do another one of those. I claim that this system also has infinitely many solutions. Negative x minus y plus 3z equals 1, 5x minus 4y minus 6z equals 13, and negative 2x plus y plus 3z equals negative 4. I want you to come up with a matrix representation for this system, put it into the calculator, get it in reduced row echelon form, and verify that the last row has all zeros. But I have the matrix in here. I'm going to review the steps again, but I want to remind you of that shortcut. If you're using the same calculator function over and over again and you want to access it, you can just do second and the enter key. Get the answer that way. But to do that from scratch, I'm going to hit second and the x inverse key, go to math, choice B, and then tell the calculator which matrix I want to put in reduced row echelon form by selecting its name and hitting enter. So the row of zeros here is what indicates that we have infinitely many solutions, and what we're going to do is translate these first two rows into equations in order to come up with the general solution. So let's try to get that general solution. The first row translates to x minus 2z equals 1. Translate that second row for me. That second row says y minus z equals negative 2. I'm going to transfer these to another screen and we'll solve them from here. In order to come up with the general solution, the recipe, I'm going to pick an arbitrary constant for z, and I like to call it c. I'm plugging it in for z because z appears in both equations, and so I can solve for x and solve for y, and then I'll have a recipe. In the first equation, I get x minus 2c equals 1, and when I add 2c to both sides, I get that x is equal to 2c plus 1. When I plug c in for z in the second equation, I get y minus c equals negative 2, and adding c to both sides, I get y equals c minus 2, or negative 2 plus c. It doesn't matter what order you write that in. And so our recipe is the first coordinate has to be 2c plus 1, the second coordinate has to be c minus 2 when the last coordinate is c. Let me write that on the first screen. I claim that plugging numbers in for c will generate solutions to the system. We're going to start by being lame and trying c equals 0. If I plug 0 in for c, we get 2 times 0 plus 1, which is 1 for the x-coordinate, 0 minus 2 for the y-coordinate, that's negative 2, and then 0 for the last coordinate. 1, negative 2, 0 should make all three equations true. So when we check it in the first one, we're plugging 1 in for x, negative 2 in for y, and we're plugging 0 in for z, so that term will essentially be gone. So we get the opposite of 1 minus negative 2. That's negative 1 plus 2, which is 1. In the second equation, we get 5 minus 4 times negative 2. That's 5 plus 8 minus 0, which gives us 13. And in the last equation, we get 2 times negative 1 is negative 2, plus negative 2 is negative 4, plus 0 is still negative 4. And so 1 comma negative 2 comma 0 is a solution to all three equations. We're going to generate a couple more specific solutions. I want you to generate the solution you get when c equals 3. A common question I get is, how do you know what to pick for c? You can pick anything for c. So if you were doing this for yourself, you can pick whatever you want. But for this lecture, I need to kind of guide you so that you can check your solution. So I'm telling you to pick 3. I picked 3 rather arbitrarily. I just didn't want to pick 1 or -1. So plug in 3 for C and see what solution that gives you. When you plug 3 in for C, you get 7, 1, 3. So 7, 1, 3 should work in all 3 equations. I don't want you to have to watch me check all 3. Let's just check the middle one. So 5 times 7 is 35, 4 times 1 is 4, and 6 times 3 is 18. So 35 minus 4 is 31, and 31 minus 18 is 13. Yeah, it works there. You can verify that it works in the other 2. Let's find another solution. Let's let C equal -4. What solution do we get there? Well, 2 times -4 plus 1 is -7, and -4 minus 2 is -6, and the last coordinate would be -4. Let's just check this in the first one. So we get 7 plus 6, that's 13, minus 12 is 1. Yeah, it works in the first equation, and I promise you it works in the last 2. Again, there's nothing magical about what C values you pick. You can pick whatever you want. Just as part of the lecture, I have to kind of guide you by picking a specific one so that we get the same answer. In a word problem or a real-world application, there might be a specific value of C that you're interested in, or a specific x-coordinate or a specific y-coordinate. So you would just pick the value of C that would generate whatever you're interested in and then find that solution. So hopefully you feel comfortable using the calculator function, and now you have a little bit of exposure to these special cases where there are no solutions and infinitely many solutions. If you have questions about any of these examples or any of the examples that you're trying on your own, please don't be afraid to reach out to me. We can talk during office hours, or you can send me an email.